So our last talk for today is from Griffin Berlstein. Griffin is a fourth-year PhD student at Cornell, working with Adrian Sampson on tools to make debugging hardware accelerators easier. And when they're not writing REST code, apparently they like thinking about programming languages and compilers or playing with their cat. So Griffin is going to be presenting their work, Stepwise Debugging for Hardware Accelerators. You ready?
Awesome.
Great, Griffin, the floor is yours.
Okay, thank you so much. I'm super excited to be telling you all about our tool Cider, which is a simulator and debugger. So, we all know accelerators are cool. I don't think I have to convince you all of that. But when we're talking about making an accelerator, what we're really doing is taking a specification of what we want it to do, which can either be formal or informal, and somehow getting it all the way to an actual accelerator. If you happen to be a hardware expert, you might do this directly by writing Verilog by hand. If you happen to be anyone else, though, that's probably off the table. And we might use something like HLS or something like an accelerator design language, which is a high-level language that lets us write simple programs and then have them compiled through usually some intermediate representation into RTL, and then we have an actual accelerator. This is really nice, but the problem is what happens when we have a bug? Let's see what debugging looks like. So we're going to be using this as our example of our accelerator design language source code. Very simple. We have two arrays, x and y, and all we're going to be doing is iterating over that, and for each index, we're going to be doing x times 2 plus y, and then factoring out via a mask. So very simple. So what happens when we need to go debug this? If we're working in software, it would look something like this. This is basically what we'd consider, say, table stakes for any sort of software debugging. And to highlight some things about this, for one, we were able to see exactly what line we're currently executing. We're able to inspect state in fairly nuanced ways. We have all the state in our program over on the right, and then we can also set specific watch points if there are values we think are important to be able to find the updates on that pretty easily. We're also able to set breakpoints, that's the little red dots over on the right, and advance through the program and pause it so we can continue until we hit a breakpoint, or we can single step. And just to make this really clear, the unit of time we're thinking about when we're using these tools is really a program statement. Like, if we're currently on line 9 and I step the program, I expect to be on line 10. I don't expect to still be on line 9. And these tools are operating live during debugging, right? I am able to pause the program, and I am able to continue the program at my leisure to understand it. Unfortunately, we're talking about debugging hardware, and so it looks a bit more like this. If you're not familiar, this neon spaghetti is a waveform debugger, and what we're looking at is basically a trace of every single signal at every cycle for every single piece of the program. So it's a lot of information, and it's operating post hoc. So we run the program, it will vomit out this huge trace, and we ingest it into something like this and hopefully try to figure out what is wrong with it, if anything. And just to highlight a few pieces of this that are important, the unit of time we're really dealing with in this domain is a clock cycle. It's that one of those oscillating square waves over there. There's not really any high-level control. In order to map what we're seeing in signals back to our high-level program, we have to find the finite state machine that's encoding our program and just know what state 1 corresponds to with respect to our control. And so working with this means we're really considering these very narrow vertical slices of time and slowly shifting that to try to understand what's happening. But of course, like not to leave it unsaid, clock cycles are way too fine a granularity for this. It might take many, many cycles to do a multiplication or a division. So single stepping through these is really low level. So obviously, the question I want to ask is really, when we're debugging generated hardware, like, is this the best we can do? Are waveforms really the best tool we have? And the key thing I've underlined and highlighted there is we're talking about generated hardware. Like, you might wonder with the waveforms, okay, what if I just had a fancy waveform stepper that could look through it in single slices and not have to operate it on post hoc? Would that make you happy? And maybe that would be more useful, but it doesn't solve that fundamental problem I mentioned earlier of just time being really difficult. And so, of course, I'm going to contend that, yes, I think we can do better, but that to do that, we really need to address this fundamental problem of time. Like clock cycles are far too fine-grained for us to meaningfully map that back to our surface program. So we need something a bit coarser. And our solution to that is really to look at the application or accelerator design language and its intermediate representation. Because we have all the control information we need at the accelerator design language level, and it all gets encoded into structure by the time we get to Verilog. So rather than trying to reconstruct that, we should just use it directly. And so this is where we're situating our tool. Our tool called CIDR is a simulator and debugger that's built at the level of the Calyx intermediate representation. That's that in the middle, which is an IR designed for accelerator generators that combines the explicit control of the front ends with the explicit structure we'd expect from RTL. And so let's take a look at how Calyx is put together, and then we can talk about how we simulate it. So we've got, again, our little example program on the right, and we've got the outlines of a Calyx component on the left. This is the base structure we have things in. And there are three main pieces of a Calyx program. We've got cells. These are the explicit declarations of all the pieces of computational element in our program. So for instance, we have a standard memory, which is realizing our array X. In this case, I've also explicitly instantiated a register for our value I. And importantly, we also have to instantiate things like the adders we're going to use explicitly, and the multipliers and so on. There's a bunch not listed up there. The second piece, which is also part of this explicit structure, is groups and wires. So these are really bundles of assignments. And here we've got a handful of groups. You can see we've got the update index group on the right, which is handling this incrementing for our index. We also have a multiply here, so that's do mult, and an addition, so that's our do add. And I'll show you what these look like inside in a second, but the way to think of them is as these basic blocks of RTL that we care about. And the final piece is the control program, and this is really what's going to let us do what we want to. It's basically an imperative program that's scheduling these basic blocks, these groups. And so in this case, we have a sequential composition with a big while loop in the middle that's doing the iteration from our program. And so, all right, let's blow up a group and find out what's inside it. So inside a group are really a series of assignments, and just think of these as RTL assignments. And in this case, I'm showing you simplified insides of the update index group. And this really maps to effectively realizing this tiny circuit where we have an adder and we're just incrementing a value in a register. And so that's all the pieces of Calyx. That's all you need to know. Don't worry if you don't have the details down 100%. And so how are we going to simulate that? That's really our question. Here's what it looks like. So I've blown up a bit of the state here. We have a sequential composition of groups on the right, and we're going to look at simulating a single group in our chain. So we start at do mult, and to simulate this, we're basically doing the very standard simulation. We're evaluating every assignment in our group, which we've seen it's a list of assignments, and we're going to do that until it converges. This is just very standard delta time. Then we advance by a clock cycle, and we repeat this process until the group is done. And once we've done that, we're basically stepping through at the level of a clock cycle still. We're just ticking up the time until eventually we're done with the group. And then we move. And so now we're at do add. And then the process repeats. And so eventually we get to compute mask, and then eventually we're finished. And so these are really two granularities of time. Over on the left with stepping, that's still clock cycles. That's still really, really coarse. And of course we need to have this in order to be able to do the simulation. But really we want to be operating over on the right side, stepping over groups and really saying, instead of advancing from do mult at time 0 to do mult at time 1, I'd really like to be able to say, well, let's advance over do mult and see the results, rather than stepping through the individual sub-pieces. And so, of course, we have stepping available at the fine-grained level when necessary, but whenever possible, in order to really think about our high-level program, we want to use the group constructs to help us winnow down what we're looking at. And so to zoom back out for a second, we can really look at this mechanism. So stepping over a group really just means we are running our program until a group is not running. Comparing this with a breakpoint and a continue statement, that is doing running the program until a group is running. These are basically opposites. And just to point out the obvious, this is the same mechanism. Like, this is all built on knowing what group is executing and when. But this lets us build a lot of very cool things. So for instance, the second we have breakpoints and continues and the ability to print state, now we can have watch points. because all that is setting a breakpoint, continuing until we hit it, and printing out some information before moving on. And on top of this, we also built some rudimentary source line ascription. So basically what we did was attach these little position tags to each group. And so then knowing what group is executing means we can ask the program, we can ask CIDR really, where are we currently, and print it out. And that looks something like this. So in this example, I set a breakpoint on our index update, continue to it, and then if we ask where we are, we can see the source level information. And so that's how we build these debugging features. Pulling it all the way back out, we can look at one way we might inspect an overflow bug in this program. People might have missed it. It was going by very fast. But if we did 2 bits for our index in that program I showed you, it'll actually be caught in an infinite loop, because while that's enough to count up to 4, we're actually never able to tell that our loop finished terminating, or finished so we could terminate. So instead, if I were to observe this directly, we can set a watch point on the out value of our index and say, I want to see the value after every update. This is basically equivalent to picking a bunch of vertical slices that I know the value is going to be relevant at. And then it'll print it out with some nice formatting. To talk a bit about the overall improved debugging experience in the ecosystem, we can do stuff like this, where having explicit print statements, while far from revolutionary, has actually really helped us in a lot of our own programs, just because interpreting state is actually really annoying sometimes, and CIDR supports a handful of these format flags to just make that easy. We also found that because we have an interpreter, because we can just run Calyx programs on CIDR directly, it helped really tighten that loop from trying to prototype a new language to getting any actual feedback on it, finding errors much more quickly. And most excitingly, at least in my opinion, is we're able to address undefined behavior at the level of the Calyx semantics itself, as opposed to allowing things that Verilog says are okay, but we really don't want to be in the language semantics. So for instance, memory addresses, you can actually provide invalid indices to memories in Verilog, and that's okay for some definition of okay. Whereas in Calyx, we really want to outlaw that entirely. Like, there's no reason your accelerator generator should be misindexing memories. We have a number of case studies, which I don't really have time to go over, but we did do we found several bugs using our tool and walked through all the details in the paper. Because people are probably curious, just a quick look at performance. We are 4 times faster than Icarus Verilog, which is an interpreter, and we are 3 times slower than Verilator, which is a full cycle compiled simulator. So that's CIDR, and I'm now ready to take any questions.